Alrighty, geometry, we are going to do a combination of ideas that are coming out of section 9.3 and 9.4, but since I already had, I think, a 9.3 and a 9.4, I'm not really going to give this a section number or a section title, and it's going to have a worksheet with it anyway. So we're going to talk about two different types of symmetry in this video. We're going to focus first on reflectional symmetry, where we're going to really talk about lines of symmetry. And I kind of feel like a kindergarten teacher because I've got all these different shapes that I've cut out, and I don't think I ever want to be a kindergarten teacher. That would not work for me. They don't understand sarcasm. Like, what would I do? So I'm going to start off with the shape of a leaf. I'm kind of giggling. My mom worked with kindergarten kids for years, and she's like, yeah, you don't have the patience for little ones, so I decided to work with the bigger ones, you guys. So let's talk about how we can find a line of symmetry. So basically a line of symmetry is where we cut something perfectly in half. Well, if I were to take this leaf, if I could pick it up and fold it, that's not exactly in half because the base and the point, they don't match. Or if I fold it like this, that doesn't match up. But if I were to fold it, keep in mind, I'm the one that cut this out, so it doesn't get cut quite perfectly. I can't cut perfect across the lines. If we were to fold it right there, from the top point down to the base of the leaf, it matches up on itself. It folds directly onto itself. That means that it is symmetric. And specifically, I'll get my ruler, we have a line of symmetry that is cutting right through this. So one line of symmetry where we could fold it in half and it would map directly on top of itself. Well, when we think about the concept of symmetry, this word reflectional, see how it reflects over the line of symmetry to match on itself? That's the concept of reflectional symmetry. And what I just drew is a line of symmetry. So I'm going to draw you guys a bad picture because that's what I do best. I want to draw my attempt at a square, and that's not that bad. I've had much worse, as you've seen. So when I look at the square, how could I cut it so that it would fold on top of itself? Well, I think it would make sense that I could cut it in half from right to left and fold it. And I'm going to have my square, this one's just a bigger version of a square, and show you that, yeah, we could totally fold it and it has symmetry. If we folded it bottom to top, there is another line of symmetry. Well, what if we folded diagonally? Now I feel like I'm doing origami. I did that once when I was a kid, a couple times actually. Hey, we have that matching right on top of it. So this has another line of symmetry. And then if I were to fold it this way down, hey, look at that. This guy has 1, 2, 4 different lines of symmetry through the middle, top and bottom, through the middle, left and right, and on the diagonals. And so what I've modeled for you is how we would sketch a line of symmetry. Well, maybe we should take a look at the butterfly. So how many lines of symmetry does the butterfly have? Well, if I fold it this way, wing to wing, hey, that works. If I fold it this way, not so much. So this butterfly is going to have one line of symmetry. So when we take a look at our assignment that you guys are going to have, and I'm going to step away from my docking camera for just a sec. Sorry guys, I'm trying to find where I printed that, and I know I printed a copy because I wanted to do some examples with you, and of course it disappeared off my table. Well, I guess I will do examples as needed. Darn it. Well, sorry to waste your time. Alright, moving on. So, that's going to be the first part of your assignment where you guys are going to need to sketch lines of symmetry. But not everything has a line of symmetry. So here's another one. Now this guy is what we call a parallelogram, so think of a rectangle but on a slant. Well, does this one. If I fold it that, no, that's not going to match up. If I fold it this way, that's hanging over. If I fold it this, even though this looks symmetric because it's got those, parallel sets of sides, this guy is not going to have any line of symmetry. So sometimes that happens and we have to be very aware of that. Not everything is symmetric when we talk about reflectional symmetry. So the next type of symmetry that I want to address with you is the concept of rotational symmetry. Okay, so to rotate means to turn, and symmetry means to turn back onto itself. So I've got a couple of different examples that I'm going to use. I just have to get all of my little papers lined up. So I've got an equilateral triangle that I cut out. This is actually a cereal box. I just needed some cardboard. And an equilateral triangle is telling us that all three sides are going to be the same length and all three angles are going to be the same measure. And then I have another equilateral triangle that's just a little bit bigger. Okay, so the reason that I have two of them, I want you guys to see how they're going to match up. I'm not saying that these are the same. They're obviously not. One's bigger than the other. What I want you guys to think about, pretend that there is a point right there in the center of my cereal box equilateral triangle. So at the center, if I start turning that, how many turns do we have to go through until it maps right back onto itself? And the reason I have the bigger one is just so that you can see when the corners are going to get where they belong. Well, if I do that again, one turn didn't work, but two turns did. Interesting. So this has a concept of rotational symmetry. Very interesting in this concept. Well, does everything have rotational symmetry? Well, let's talk about our leaf. How far do I have to turn it before I map it back onto itself? How many degrees am I having to move? So I'm going to start that again. I'm going to focus on the point, okay? How many degrees does this point have to move? And you'll notice I keep my finger kind of close to the center until that point gets right back to itself. As that took a full circle. That was 360 degrees of a rotation. Interesting. So does it have rotational symmetry if it has to go all the way around a full circle to get back again? That sure doesn't really feel like a rotational symmetry concept. Well, what about a square? And let's see. I think I have a different square so that you guys can see when it matches up. Well, how many turns does it take to get there? That looked like one turn. If I number my corner right here, corner number 1, that's one rotation. Out of how many would we have to do? 2, 3, 4 to get it back to its original position. But in one rotation, we can have symmetry where it maps back to itself. But there were a total of 4 turns. So with this square, assuming it's a square, like pretend I cut out everything perfectly and measured and all the sides are the same. With this square, we are moving 1/4 of the way. So I'm going to draw myself a square. For us to map that corner down so that we have symmetry, we have 1 turn out of 4 if we were to get all the way back to the original location. Well, guys, there's 360 degrees in a full circle. What we're going to do is we're going to multiply that by 1/4 of a turn. Well, 360 times 1/4, 360 times 1/4 is really 360 divided by 4. That's 90 degrees. This has rotational, technical difficulties, make sure my computer doesn't stop, rotational symmetry at 90 degrees. It takes a 90-degree turn to make this land back on itself. Now granted, that corner's not in the same spot. That would take 4 rotations. But 1 turn, 1/4 of the total way around, gets you symmetry. So let's see if we can think of some others. Let's go back to this triangle. And I'm going to mark the number 1 up here on my triangle. Try to keep my finger in the center without keeping it in the way of the view. How many turns does it take to get us to where we match back? 1 turn and I match. 2, 3 turns and I'm back to the original. So for this triangle, yes, it does have rotational symmetry, but it's taking 1/3 of the 360 degrees to get there. Interesting. Well, 1/3 of 360 is 120 degrees in its rotation. Well, now let's play with something else. Let's do another shape. I've got so many different shapes. Let's do a whale. Yeah, I literally printed a picture of a whale and I cut it out. All right, so kind of there's my center. Well, how many degrees do I have to move, come on fingers, before I get back to mapping on? That's 360 degrees. That's boring. Let's do this guy. Now this guy, I think this is a pentagon. 1, 2, 3, 4, 5 sides. All right, so I have my shapes here. I'm going to put the pentagon on top of itself, and I'm going to put the number 1 here. How many moves do I have to make until I get to mapping back on itself? That was 1 move. So from one vertex to the next, it automatically maps. This pentagon is going to have rotational symmetry. I'm going to do my best to draw a pentagon. It's not quite perfect, but it's good enough. And it's a regular pentagon, so all 5 are the same. But we did 1/5 of the motions as we turned, we mapped back onto itself, 1/5 of 360 degrees. Yes, I'm using my calculator. That is 72 degrees of our rotation. Interesting. Let's do, I think I have a hexagon somewhere. That's a heptagon. Where's my, there it is. Let's do the hexagon. So here's my hexagon. I'm going to mark a point, a corner, a vertex right there at 1. How many turns until I get it to map perfectly? 1 turn. As soon as I made 1 vertex turn to the next vertex, that matched back to itself. It has symmetry. So for our hexagon, again, regular hexagon, all 6 sides are the same. It was 1/6 of our 360 degrees. So that is a 60-degree rotational turn for rotational symmetry. Okay, I'm hoping this is matching and making some sense. I'm going to do an apple. Yeah, that apple doesn't rotate back to itself until we get 360 degrees. That doesn't really work. Ooh, I kind of hope that's making some sense. Let's do a circle. Too much writing on my paper. Turn the page. What about a circle? Put my center point. Does it ever stop mapping back on to itself? Sorry, my fingers are in the way. No, it really doesn't. This has infinite rotational symmetry. Interesting. Okay. So your guys' task, you're going to have a PDF. At the start of the PDF, and I know as soon as I finish my video, I'm going to find my copy of that PDF that I printed out. So on that PDF, you're going to have problems that are going to ask you to draw in lines of symmetry. So again, these are lines of symmetry. Not everything is going to have a line of symmetry. I could give you an example of a trapezoid. No matter how I attempt to cut that baby, it doesn't have a line of symmetry. So remember, a line of symmetry is where it folds back to map upon itself. And then you're going to have another set on the bottom where it's going to talk about rotational symmetry, whether or not it has it, and how many degrees we have to rotate our shape to map back on to itself. So it's a little over a 15-minute video, but hey, I've given you guys worse. As always, let me know how I can help.